Okay, let's talk about the unit circle a bit. You're probably used to seeing in trigonometry, if you've ever taken a geometry class before, the idea of the right triangle trigonometry. So you have, oops, I need a pen. There you go. Right triangle trigonometry, where you have, bear with me, pretend that's a right triangle. You have an angle, and you have the mnemonic Sohcahtoa. Some of you may have seen this. And we introduced this in right triangle trigonometry. If this is my angle, here's my opposite side, here's my adjacent side, and here's my hypotenuse. And so the sine of this angle is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is opposite, O over adjacent A. So I'm not going to go into right triangle trigonometry here. I'm going to focus this presentation just on the unit circle. So, because that is kind of a new approach for many of you, and some of you may not be used to seeing the circle approach. But as you can see, it involves the right triangle approach. I have a right triangle. Drawn inside this circle, and let me just point out several things. First of all, what is a unit circle? Well, a unit circle is basically, it's a circle with equals, that's not a plus sign, equals. It's a circle with a radius of 1 and the center at the origin. So my center is at the origin. And so let's think about what that means. Well, let's think about the lengths of the sides of the circle. First of all, so I have points 1, 0 on that circle, 0, 1. And this is just a generic XY point. This could be up here, it could be down here. This refers to any XY point on that circle. So this is just a generic point. So let's think about let's look at the lengths on this right triangle. Well, what's the length of this hypotenuse going to be? Well, the length of this hypotenuse, let's see, it's a circle of radius 1, and this hypotenuse is a radius. So, therefore, the length of this hypotenuse is 1. The length of this long side, well, let's see, we go from y equals 0 to y equals y, so y minus 0, so this length here is y, and this length here, just not the whole radius obviously, but just from here to here. This length here of the triangle is going to be x, because we're going from 0 to x. That's this horizontal distance. So let's think about our right triangle. Oh, and this is theta. I should zoom in on this a little further. Okay, so let's think about sine. Okay. Sine of that angle theta. Well, if sine is equal to opposite over hypotenuse, see it's Sohcahtoa here, it's on this side, it's opposite over hypotenuse. So what's the opposite? The opposite is y, and the hypotenuse is 1, so look at that. Sine of theta equals y. And you could say the same thing for cosine theta. Right, cosine theta is the adjacent side. Well, the adjacent side is x, the hypotenuse is 1. Is still 1, so cosine theta is equal to x. And of course, tangent theta, well, tangent is equal to sine over cosine, so that's going to be y over x. So that gives us a very useful set of identities here. And also, I want to talk about one other thing before we move on, and that is the Pythagorean identity. Yeah, gotta excuse my handwriting here. Pythagorean identity. Now, of course, the definition of a unit circle, as I told you, x squared plus y squared equals 1. But you look, we also have a right triangle here. And so, you know, the Pythagorean theorem, that's where the word Pythagorean identity comes from Pythagorean theorem. X squared plus y squared equals 1 squared, and of course 1 squared is 1. So I can write this x squared plus y squared equals 1, and because x is equal to cosine of theta, and y is equal to sine of theta, just in case you're wondering about this notation here, if I have sine of theta, the whole thing squared, we're generally going to write that as sine squared. We're going to put the exponent over here. Same thing goes for cosine and tangent and all the others. Okay. So there's one of your Pythagorean identities. There are others, which you'll get to a little bit later. But that's very important Pythagorean identity, as well as these. Yeah, as well as these. So these and your Pythagorean identity. Those are very important to remember. Okay, the next thing we should talk about is the idea of angles of a circle. Now, the way you're probably used to seeing angles is in degrees. So I can take from here, from one point on the circle, and go all the way around, and that is 360 degrees. But you'll see that in pre-calculus and as you go into calculus and higher, you're not going to see degrees very often. You're going to see radians. And so we need to talk a little bit about radians and what they are. Without getting too complicated, I'm just going to say this. If you have a circle, let me erase this because it's kind of messy. Draw a new circle here. If you have, I need a circle, that's why. Oh, that's better. Okay, so if you have a circle, and I have, so here's the center, and I have a radius here, and a radius here, and I'm going to call this S. This is the distance of an arc that's in between these two radiuses. Okay. And of course I have an angle theta here. So I'm going to say if S is the length of this is equal to the radian, then this angle is 1 radian. That's as far as I'm going to go into definition of the radius, but definition of radian. But that's basically what we're looking at. And so let's think about the circumference of a circle. Okay, so the circumference of a circle, where's my pen? Circumference of a circle is, we know, or we may remember from geometry, is pi times the diameter. Of course, what's the diameter? The diameter is 2 times the radius. So the circumference is 2 times pi times r. But let's remember, in a unit circle, if it's a unit circle, then r is equal to 1. So the circumference is going to be 2 pi. So 2 pi radians, and normally you're not going to see, if an angle is expressed in radians, you're not going to see the word radians or RAD written out. Generally, if there's no degree symbol, you're going to assume the angle's in radians. But this is going to be equal to 360 degrees. So based on that, let's suppose we need to convert between radians and degrees. Well, 2 pi radians, 360 degrees equals 2 pi radians. Part of the pi there equals 2 pi radians. Therefore, I can say two things, two conversions. I can say that 1 degree is equal to pi over 180 radians. I could also say that 1 radian dividing both sides by 2 pi is 180 over pi degrees. We'll put in a little parentheses around here. So that's the conversion you can make. So, for example, let me go up to the side here. If I want to take 45 degrees, I need to take 45 degrees and convert it into radians. Well, what I'm going to do is just multiply. Well, let's think about this one. If you get these two mixed up, when do you use pi over 180? When do you use 180 over pi? Well, here's a way to think about it. The number of radians, the angle measure in radians is always going to be smaller. So how can I make this smaller? Well, I can multiply. I keep losing my pen. There we go. I can multiply by pi over 180. And of course, now that we have degrees here, this degrees here will cancel out with this degrees. And so I get pi. This will simplify to pi over 4 radians. And like I said, normally you're not going to see radians written out. I would just write this as pi over 4. But that's how you convert degrees to radians. And, well, radians to degrees, let's say pi over 6 radians. I'm running out of room here. Pi over 6 radians. Well, I want to make it larger. So that's 180 degrees over pi. So again, pi's cancel out. 180 divided by 6. Pi over 6 radians is the same thing as 30 degrees. Okay, so that generally gives you an idea of unit circle, Pythagorean identities, radians, degrees, and the appropriate conversions. I'm going to make another video after this. We're running out of time for this one. But I'll show you basically how to find angles, how to find it. Your book makes a mention of degrees and T and P and terminal points and that type of thing. So I'm going to try to straighten that a little bit out after this.